The Auerbach-Kotlikoff Model, Economic Model and Computation, Part 2, Value Function Iteration. Hello and welcome back to the second part of our video tutorial here on the Auerbach-Kotlikoff Model. We have analyzed a 60-period overlapping generations model, where each period corresponds to 1 year. So we have 60 different cohorts alive in each period, and we studied the steady state. Therefore, we had to solve the individual optimization problems, which was a complex problem, can be described with the help of 99 nonlinear equations and 99 unknowns, and we used the Newton-Raphson algorithm in order to solve it. Now, this algorithm was fast, this method was fast and reliable and accurate. But unfortunately, it's not always possible to use it. So in the case of more complex problems with very heterogeneous agents, with a high number of possible paths for the individual profiles on consumption and wealth, this might become too much of a computational burden. So we have to rely on other methods. And one possible method that we will look at today is value function iteration. It relies upon the discretization of the individual asset space. So we do not just compute the profile for one individual, then for the next, but we just compute something like a policy, called a policy function. So this gives the optimal next period savings, the next period wealth level, and then optimal labor supply as a function of the individual state space, which is, in our case, just wealth. So we only need to keep track of the wealth level of the individuals and how many people, for example, hold a wealth of 1.0, 1.1, and so on. And this will help us to compute the resulting equilibrium much easier. So let us get back into the model. Let me just briefly review the characteristics, equilibrium conditions of our model before I introduce you to value function iteration. So please load the slides for chapter 9.1 from the book Dynamic General Equilibrium Modeling into the computer and follow me through the slides here. This chapter is taken from the book that I've written with Alfred Mausner, Dynamic General Equilibrium Modeling, Computational Methods and Application, in particular chapter 9.1. So let us briefly review the model. We have a household that is born at age 1, which corresponds to year 21, to the year 20 in real life. He works 40 years, then retires 20 years. His labor supply as a worker is denoted by LST, his labor supply at age S in period T. And his lifetime utility is the sum of the utilities over the different years, over the different periods. And the discount factor here is beta. So utility at age S in period T is a function of consumption C and leisure 1 minus L. We use a very simple instantaneous utility function, a Cobb-Douglas function, C in consumption C and leisure 1 minus L. And we added this constant here, psi, to consumption, so to allow for the analysis, the computation of the special case where income is 0 and we consume C equal to 0, then our algorithm, our computation does not fall apart because we do not have to consider a negative number or 0 to the power of minus 1. We have a budget constraint at young age. When we are a worker, we get labor income earnings WT, LT, which are taxed at rate tau T, our social security tax. We have assets AST, which yield the return RT. And we use it for consumption CS or for next period savings AS+1. In old age, we do not get earnings, wage income, but we get expansions instead. And we have derived the first order conditions here, 5 and 6, and solved them. Now let's get to value function iteration here. Before I present to you the idea of value function iteration, we need to consider two additional elements that we will look at, that we will need in our value function iteration. One is linear interpolation, and the other one is an optimization routine in one variable, golden section search. So let me briefly describe linear interpolation. We will have, for example, an optimal policy function, labor supply or savings or consumption, as a function of the individual asset here. So we basically have a function f of x with the argument x. And we will store the optimal policy function at grid point, let's say x1 and x2. But of course, we also would like to compute the policy function between grid points at a point x. And here in this case, in the figures you can see, we will just do linear interpolation. So we have f of x1 and f of x2 tabulated these two values, and we just compute f of x by using linear interpolation. Of course, we are not exact, and this is of course a source of inaccuracy in this model, that we need to use linear interpolation. We cannot store our optimal policy functions here at all grid points. The second element that we need to consider is golden section search. So we want to find the maximum of our function. Let's see, we have a function f of x, and we want to find the maximum x star. And we know that it's somehow located in the interval a, d. So this is taken from the book Dynamic General Equilibrium Modeling, section 11.61, where we describe this method. But it's such a standard method in numerical optimization that any book on computational methods will consider it. Now let's assume we have picked two values, b and c. How shall we proceed? Well, we know that the optimum, the maximum, is in the interval AC. Why? Because b is the larger point. We have the larger function value at the point b. It's larger than the function value at c. So we know the maximum must be inside this interval a of c, and we use this as the next interval where we look for x star and introduce a third point. We call it b1 here. And compare again the function values at point b1 and b. Now, if the function value at b point is the larger one, then we use this interval, a1, b1, and b. If not, we use the interval b1, c1, and d1 as our next interval. Therefore, we shrink the interval around the maximum and always discard the right or left interval limit depending where the larger value is located of the two inner points. Okay, now the question is, how should we pick B and C? And there are two assumptions which are useful. Well, we do not know in advance where we end up, whether the optimal interval is AC or BD to search in the next round. So it makes sense to choose these two intervals of equal length. AC should be equal to BC, because we do not know where we end up, and we do not want to end up in a larger interval in a case that's not really convenient. So we choose these two intervals the same size, AC equal to BC. So in the next iteration, we pick the value b1. So we have the new interval a1, b1, c1, d1, and compare b1 and c1. And again, we should have the same principle that a1, c1 is as large as b1, d1, so that we do not end up in an unfavorable interval which is larger than the other. So it should copy the proportions of a, b, c, d should also be the same proportions as a1, b1, c1, d1 in the next step. So the lengths of AD relative to AC should be equal to A1, D1 and A1, C1. The same holds if we end up in the interval, if the maximum, for example, lies here, and we end up in the interval BD, that the length of A2, D2 and A2, C2 is equal to AD and AC. When we impose these two restrictions on our procedure, we find that there is an optimal ratio of the distance AD and AC, the ratio of these two distances. And this distance is called the GAUSS ratio, and it is equal to 0.618. Now, the advantage of this method here, the GAUSS section search, is that it's really reliable and converges to a relative maximum. Of course, if we have many maxima, well, we can end up in the wrong one, but if we have a well-behaved value function, and this is the case mostly, at least here in our application, this is the method that's reliable and robust. And we will use this method, GAUSS section search, in our optimization routine. Okay, now we provide a function in MATLAB that's called GAUSS and a procedure in GAUSS that's also called GAUSS, where you have to provide the function f and the interval points a, c, and an intermediate point a and d, and an intermediate point c. And from then on, this GAUSS section search will find the maximum with a specified accuracy. Now let us go into the value function problem. And consider the lifetime utility of the household at the age 1 in period t. We look at the steady state, so we dropped the time index. And here in 21, we have just the discounted lifetime utility over the 60 periods of the newborn household, subject to the budget constraints. And given initial values A1 equal to 0 and final values after that A61 equal to 0. Now let us call US the controls, and the state variable notice that our state variable is the individual wealth level AS. Our control variables in this problem, in this optimization problem, are the labor supply and the consumption at age S that we can choose in order to maximize our lifetime utility. Now let's define a value function. A value function is the greatest feasible lifetime utility from age S forward to the end of the life in period t. So formally, the value function is the supremum of the lifetime utility for the remaining years. So we are S years old, and we just sum up the instantaneous utility from age S on until our final period of life, uppercase t, and sum it up and discount it with the factor beta. Here we have the supremum. In our case, this is equal to the maximum, so we have well-behaved utility functions. We have closed sets to choose our labor supply from 0 to 1, and this results in the fact that here in our case we have the maximum which is a special case of the supremum. We have well-behaved, nice, smooth function, differentiable function. So in case you're not familiar with the supremum, just assume that our problem is well-behaved and we use the maximum in the following. Now let's consider the person who's 60 years old and dies in the next period. So we are in his last period of life and he knows he consumed all his pension and all his wealth and all the interest that he earns on his wealth, because there's no need to save anything for next period. He will be dead anyway, and he has no bequest motive. He's not altruistic with respect to the next generation. So wonderful, the household knows what to do. The labor supply L60 is 0, so that his leisure is equal to 1. Next period wealth is equal to 0, and his consumption is equal to the pension income plus the interest income, R times A60, plus his wealth, which he consumes completely. So we can substitute this into the value function at age 60, which is simply the utility in his last period of life. His lifetime income at age 60, his remaining lifetime is just this one period, so the value function is equal to the last period utility function. We know how much he consumes, and this provides us with the value of the value function. Notice that it's a function of A60, of his beginning of period 60, age 60 wealth level. So his wealth function at age 60 only depends on his state variable wealth A60. Now let's look at the household who's 59 years old. His lifetime utility is the sum of utility at age 50 plus discounted utility at age 60. His control variables are consumption at age 59 and at age 60. And he faces the budget constraint that depending on his consumption at age 59 and age 60, he's left with wealth A60 and A61. And A61 again is equal to 0. So this is the value function of the 59-year-old. And now comes the beautiful insight for a man named Richard Bellman, who looked into this so-called dynamic programming problem. He noticed that you can identify, of course, the utility at age 60 with the value function at age 60, and it only depends on, as we have just seen, on the asset level at the beginning of age 60. So we can replace utility at age 60 by the value function at age 60, which is now a function of the wealth level A60, and end up with a so-called Bellman equation where we have lifetime utility, the value function at age 59 is the maximum of the sum of the utility at age 59 plus the value at age 60 discounted by the factor beta. And here we just maximize over C59, notice, because consumption at age 59 implies the wealth level at age 60, and this implies our value of the value function at age 60. So we have reduced this two control problem into a problem in one control, and we have split up, divided this maximization into sub problems where we just looked at optimization at age 59, while simultaneously determining wealth level at age 60 and therefore our remaining lifetime utility. Let us shift this problem again backward in time and get to an retiree at age S. And this age is now 41, 42, up to 49. We can decompose it into consumption at age S and instantaneous utility at age S. And consumption at age S implies next period asset, A of S plus 1. And this implies the value of the value function, V S plus 1 given for wells as of 1 discounted by the factor beta. So that's the famous Bellman principle of optimality. We break the optimization problem, which, for example, for the 41-year-old retiree is an optimization problem in 20 controls, C41, C42, C43, up to C60, into much simpler subproblems, just maximizing instantaneous utility with respect to the current controls, consumption at age S, which implies next period wells and therefore the value of the value function. So by breaking up the value function problem from a 20 or 40 or 60 dimensional optimization problem into a one-dimensional problem where we just choose optimal current period consumption CS. Of course, for this we must have computed the value function in the next year, Vs plus 1. And we will do so, and we will just store it, save it at different grid points. And when we maximize this, of course, this might be, of course, only a grid point with probability 0. So we end up between two grid points, well, and then we interpolate between our tabulated values to compute the value of Vs plus 1, of As plus 1, and have therefore transformed the problem into an optimization problem in just one variable, which we solve with goal section search. Okay, now let's go even back further in age, so go back in time and look at the worker who between age S1 and 40, and his value function is the instantaneous utility at S plus next period value of A of S plus 1 discounted by factor beta, subject to his budget constraint. So if the worker has now two controls, his consumption and his labor supply, and the two already determine next period wells according to his budget constraint, and therefore the value of his value function Vs plus 1 next year. Now, how do we solve this problem? Well, let's look at the Bellman equation of the worker and substitute his budget constraint for consumption here. So here we have 1 plus R times RS plus 1 minus tau WLS, the net wage income, minus next period wells minus AS plus 1, his budget constraint. So we have C plus S. And look at this Bellman equation and the optimality condition. So let us assume that the value function is differentiable and that maximum value is an interior value. We will look in the computer program what happens if it's not interior, but if it's at the credit constraint that assets must be larger equal to 0 binds, so that the optimal asset is, next period asset is 0. Now, but let's look at the inner solution first, interior solution first. Then we can use the method that we know from calculus, from analysis, and differentiate the function inside the curly brackets with respect to the controls ls and consumption cs, and derive our first order conditions, which are the first two equations here. So if we differentiate this equation with respect to C, we get the with respect to L, the labor supply, we get the marginal utility from consumption times 1 minus tau times W, that's marginal utility of the outer, the derivative of the outer function. 1 minus tau W is the derivative of the inner function, 1 minus tau W ls with respect to ls, is equal to marginal utility from leisure, and this is the derivative of this utility function here with respect to leisure 1 minus ls. The well-known first order condition that you already know from our Lagrangian function, exactly the same first order condition. Now when we derive the maximant here, the function here in curly brackets with respect to next period savings s plus 1, as plus 1, we get that here that marginal utility you see, that is the derivative of the outer function, and the derivative of the inner function here, using the chain rule, is minus 1, is equal to beta times the derivative of the value function at hs plus 1, vs plus 1 prime, with respect to next period as it's as plus 1. So these are our two first order conditions. And now we can apply the so-called envelope condition. So this value function is, of course, the maximum value of the lifetime utility for given state variable as. So if we maximize the value function with respect to as, the left-hand side, the envelope theorem tells us, the envelope condition, that it's equal to the derivative of the right-hand side with respect to as. So we have that vs prime as, the derivative of the value function at hs with respect to asset level as, is equal to 1 plus r times, that's the inner derivative of the inner function, sorry, is equal to beta times vs plus 1 prime of, sorry, sorry for this. So we take the derivative of the right-hand side with respect to as, sorry, not as plus 1. So we got that the derivative of the outer function utility with respect to the first argument, that's marginal utility of consumption, you see, and the derivative of the inner function consumption with respect to as, of course, is 1 plus r. So we have derived the envelope condition vs prime is equal to 1 plus r times uc at hs. Now when we lag this condition here, the envelope condition, by 1 year, so we have vs plus 1 prime of as plus 1 is equal to 1 plus r times uc of cs plus 1 times 1 minus ls plus 1, and substituted in the second first order condition, we see at once that it's our Euler equation. And the first equation here is our first order condition with respect to labor. So if we compare this to our optimal condition that we derive with the help of the Lagrangian, well, it's just the same. So we derived equations 5 and 6 from the value function from the dynamic programming problem, the same conditions, and we have the equivalence result. That's, for example, shown in Stokely-Lucas with Prescott, 1989, that these two optimization calculuses yield the same solution. Okay, so that's wonderful. No matter which approach we take, the value function iteration or using the nonlinear equations from the Lagrangian, we will end up with the same solution. In our special case here with Cobb-Douglas utility, it is very convenient to notice that if we substitute our marginal utility of consumption, our marginal utility of leisure into the first order condition of the household, our condition for labor supply looks like this. So we can derive labor supply as a function of this period wealth as and next period wealth, next year age wealth a of s plus 1. And this will be very convenient. Okay, now let's go on and present to you, let me present to you the idea of value function iteration. We want to compute the value function v s of as at hs s from 1 to 60 over the interval a min to a max. We start by choosing the state space on which we would like to compute the value function. Well, we can choose a different interval for each age, but how this might become cumbersome, it's possible. But we make a very simple assumption. We look at the same state space, individual state space at each age. So we choose a mean as our credit constraint. The lower bound of our wealth level is 0. And now we have to choose an upper wealth level. Now from our computer, from our algorithm, let me show you the algorithm here again. We have started the algorithm, remember, by specifying an initial value of capital stock and employment. And we have found that employment is approximately equal to 0.2 and the capital stock is approximately equal to 1. Then we can compute the wage, the interest rate, and the social security tax, tau. And we now do step 3 and compute the optimal path for consumption, savings, and employment, the optimal policy functions. That's the step that we describe now, the value function iteration step. Previously, we used the nonlinear equations with direct computation, used the Newton-Raphson algorithm. Now we use value function iteration. So in step 1, we computed K and L initial guesses, and these initial guesses amounted to 0.2, and the capital stock with the help of the first order condition and an interest rate of 4.5% was approximately equal to 0.8. Of course, our interval here between a mean and a max, the individual state space, must contain the average wealth in our economy, which is 0.8. But of course, we also remember that over the life cycle, we accumulate savings for old age, so our wealth will increase above level of 0.8. Well, but how much will it increase? 2-fold, 3-fold, so that's approximately what we observe in our Auerbach-Kotlikoff model. Some people just have 5 times the wealth of average wealth. Some people are very rich. So we just start with the value of 10, which is about 11, 12 times the average assets in the economy. So, of course, when we are done with our computation, we have to check if this interval was large enough, or, for example, the 60-year-old or 50-year-old or 40-year-old, whether they do not accumulate assets close to 10. This would then be an indicator that we need to increase our asset space. Now, since this is an infinite number of points in this interval between 0 and 10, we have to discretize it. So we have to choose grid points on which we compute the value function. We cannot compute it on every grid point that's in this interval because there are simply infinite grid points. So we choose 200 equispaced grid points on the interval 0 and 10, so that they are approximately 0.05 away from each other. And we can only compute the value function numerically at a discrete number of grid points. Between grid points, we interpolate linearly, as I have shown you before. So we just use this linear interpolation method here, which is very easy. We store the value function at a grid point x1 and at a grid point x2, and when we want to compute, if we want to compute the value function between 2 grid points, we use linear interpolation. And because, as we will see, the value function, of course, has the same shape as the utility function and is concave, we are off the true value, and we have of course an approximation error here. That's different in our case where we use direct computation, because we only compute the optimal policy function at the exact point, at the exact asset level of the household. There we know we only have to compute the solution at point X, and this will of course reduce the approximation error, our accuracy error in the accuracy. So that's our first choice. We choose the state space, the grid over the state space, and choose the interpolation method. We choose linear interpolation. But it's easy to modify our computer program, for example, for cubic interpolation. Now that we have determined the interval a min, a max, over which we would like to find our policy functions, our value functions, and then our policy functions, how much we should consume, how much we should save, let's go to the next step and start at the end of a person's life at age 60 and compute his value function. So we know that at age 60 we consume all our pension income pen, we consume all our interest income R times A, and of course our savings A. And we compute this for our 200 grid points AI. So from 0 to 0.05 and so on up to grid point A200, which is equal to the value of our maximum in the interval, our upper limit A1 equal to 1.0, our upper interval limit. Now we take this consumption at age 60, C60 of AI, plug it into the instantaneous utility function U of C1 minus L. We know that labor supply is equal to 0 in old age, so leisure is 1. That's the second argument of our utility function, instantaneous utility function U. And we have our consumption C60 of A1, and we can compute the value of the value function at this grid point AI. We do this for all grid points, and we are done. We have tabulated the value function at age 60. Now we go back to age 59. Therefore, we look at the Bellman equation. That's the next to the bottom equation here on slide 45. And we notice that our value at age s is simply instantaneous utility at age s plus the discounted value at age s plus 1. So for the 59-year-old, s equal to 59, we have instantaneous utility at age 59 and the tabulated value of V60 that we just looked at. So again, we use a grid over the asset space at age 59, A59, our 200 grid points, starting from A59 equal to 0 up to A59 equal to 10, our upper limit of the individual state space, compute the solution to this value function, so the maximum of the right-hand side of the Bellman equation, with the help of an optimization calculator, and that's our GAUSS section search. So we have our given grid point at age 59 AI, and we just look at the maximum of AS plus 1, which yields the maximum value of the right-hand side of the Bellman equation, which is the term in the middle of the slides 46, pension plus 1 plus R times AI minus AS plus 1 plus our number psi times leisure, which is equal to 1, plus beta times the next period value function. And we do this over a search over AFS plus 1. So this is an optimization problem in one variable. We use GAUSS section search and find the optimal next period asset AS plus 1 for each grid point AI, the wealth level at age 59. And we save these solutions as our policy function. So for our wealth at age 59 at point AI, we know the optimal policy function AS plus 1 and CS. And we also, of course, tabulate the values of the value function at age 59 at all grid points. And so we continue backwards in time, backwards in age, going from age 60 to 59 to 58 and so on. For the working agent, when we have age equal to 40, it's the first time that the agent also has endogenous labor supply, so we have an additional control labor supply. How do we deal with this? So here is the right-hand side of the Bellman equation that we would like to maximize for the working agent at age 40. So he gets wage income 1 minus tau WLS, interest income R times AI, the grid point that we consider, plus, of course, the wealth at the end of the that's left, AI, minus next period savings, AS plus 1 plus C. We have the labor supply 1 minus the labor supply LS, which gives us leisure 1 minus LS. And we have the tabulated values of next period's value function at the grid points AS plus 1. So what we do is we substitute our labor supply, our first order condition of the labor supply in this equation. And then it's simply, in this term. And then this term is simply a term in the one variable in AS plus 1. Now, we use again GAUSS section search to find the optimal value. The value might be between two grid points, AI and AI plus 1, and we interpolate linearly the value function between grid points and store again the optimal value function as a function of the state space, which is our individual wealth. Notice that we impose one more constriction here. So far we have been a little sloppy on the optimization problem. We also have to check if our optimal condition here for the labor supply implies leisure that's larger, the labor supply that's smaller than 0, so that our leisure increases above 1. In fact, this is actually possible for particular values of AS and AS plus 1. This may happen in our value function iteration problem. This was absent in the nonlinear equation problems because our optimal wealth level did not imply such a solution. But when we search over a whole grid, this is a possibility. So we always have to check that we choose the maximum of 0 and the right-hand side here, the second argument of this maximum function, which is our solution from the nonlinear equations problems without the constraint L larger equals 0. So L equal to 0 may bind, and we have to consider this. And again, we store the value function as a function of the asset space. And now we also store the additional policy function, our labor supply. And again, our optimal labor supply, as you can see from this equation here, is only a function of the individual labor supply at age S. Okay, and this describes the whole value function iteration problem. And we are done once we have computed the value function at age 1. Okay, and then it's easy to aggregate the capital stock and the labor supply in step 4 of our computational algorithm. Let's go back to the algorithm here and of our steady state. We have now computed the optimal path, the optimal policy function for consumption, savings, and employment. And now we have to compute the optimal path, the life cycle profile. But we know that in the first period at age 1, A1 is equal to 0. So we can use our results from the value function iteration, our policy function, compute next period value of our wealth A2 from the policy function with respect to savings. So this provides us with a value A2. Again, we can use this value of the wealth at age 2, use our stored policy function, which we have tabulated at a finite number of 200 grid points. A2, of course, lies between two grid points with the probability does not lie on a grid point, but between two grid points. And therefore, we again have to linearly interpolate our policy function for next period asset for our savings. And we continue like this and can compute the life cycle profiles for consumption, savings, and employment, and simply look at the average of these values to get aggregate capital stock and employment update our guess of capital and labor, and return to step if this is not equal to our initial guess, and just iterate over the aggregate capital stock and employment as we described in the previous video. So let us look at our results here. First, let me comment on the runtime. With GAUSS, the computation with 200 grid points needs 32 seconds. If we increase it to 2000 grid points, it goes up to approximately 2 to 3 minutes. When I use MATLAB, and I use the exact same command, so I translated my GAUSS computer program into the MATLAB computer program, one by one, in a congruent fashion, then the MATLAB version from the year 2014, the release 2014, takes approximately 1 hour, 56 minutes on my computer. So it's about 120 times slower than GAUSS. And when I take a more recent MATLAB version, a release from 2019, the computational time goes up to 27 hours, more than a day, to compute the solution with value function and 200 grid points. So MATLAB is very slow, especially the more recent version, let's say from 2019 and from 2014. Therefore, I always work with the 2014 version. For more sophisticated problems, I do not use MATLAB. I mostly use GAUSS, and my co-authors often use Julia or Python and Fortran. So Julia, for example, is even about approximately 10 times faster than GAUSS, so you need just 2 or 3 seconds to compute this value function iteration problem. And you might want to consider this if you go on and try to compute very complex value function problems, for example, not just in one individual state variable like asset space, but for example in multidimensional state space where, for example, accumulated contributions to the pension system might also become a state space variable. Now let's look at the accuracy, and therefore I have computed or graphed the consumption function here for 200 grid points, which is the black line here. And as you can see, it still oscillates in old age from year 60 on. And I have to increase it to 2000 points here, the asset grid, the individual asset grid, to get a smooth linear function of old age consumption. We know from our Euler equation that consumption in young age and in old age must rise linearly with a constant slope that's implied by the Euler equation. And to achieve this, we need at least 2000 points here. So this is a good way to check the accuracy of your computer program. Consider solutions for different number of grid points. And then, of course, you also have to compute the wealth age profile. And we know this from, I haven't computed this for value function iteration, but for our direct solution method. And you can see here that the individual wealth level increases to a level to 1.7. So our upper limit on the individual state space equal to 10 was large enough, and we do not hit the upper limit. So that's reassuring. But after this exercise, we know, okay, we should use more than 200 grid points. But you should start with a low number of grid points in case the computational time is so exorbitant, as we just saw in the MATLAB version here, the recent MATLAB version. You don't want to wait weeks or months to find for the computer program to find a solution. So just start with a small number of grid points and then increase it so that you get an accuracy that you're comfortable with. Okay, so let me summarize what we find here from value function iteration. value function iteration is slow. It is very slow. Whenever possible, well, try to use direct computation with the help of the nonlinear equations that characterize our equilibrium. And you will find videos in this course here, in later sequence here, which looks at a much larger scale OLG model with a couple of hundred endogenous nonlinear equations and endogenous variables. So we will consider this for much more complicated problems than the one we do consider here right now, and still find a solution. But sometimes you can't help, but you have to use value function iteration when the number of heterogeneous agents in our model becomes too high. If we have, for example, income uncertainty, or so many different agents. For example, we look at family economics, people who have children, people who do not have children, people who become entrepreneur, stuff like this, and different productivity levels, and of course, stochastic individual productivity levels. Then you have to switch from the direct computation to value function iteration, and then you sometimes get into the place, get to a point where you notice, well, you simply cannot solve it due to computational restrictions if your individual state space is too multidimensional. So we had an individual state space which had just one continuous variable, which was wealth. But there might be additional elements, additional variables that might enter your state space. For example, if we look at pensions, and the dependence on your pension will depend on the contributions that you undertake, well, you also have to keep track of the accumulated pension contributions, a second state variable. Or if we look at a model with endogenous human capital, some people might go to high school, others to universities, others do a PhD or a postdoc research, and then you earn experience while you're working. So you accumulate human capital, and this might also become an additional state variable. And there are other examples of state variables. For example, your health. If you keep track of your health level, and there might be shocks to your health, you might have become in bad shape, stuff like this. So our state space, our individual state space might have too many dimensions, and if we have 3, 4, or even more dimensions, we failed, at least with current computer technology, to compute the solution with an adequate accuracy. Okay, so that's the drawback of the value function iteration. It's too slow, and we only may consider problems, well, in my experience and with current computer technology, 2 state variables, individual state variables, which are continuous, like, for example, wealth and contributed pensions, are usually enough. 3 state variables is sometimes already beyond the computation, especially if our function is not really linear, but we have to approximate it at many grid points. If we have an individual state variables, we will just need 3 or 4 grid points because our policy functions are rather linear function of the state space, we are fine. But if we have a lot of curvature, well, then we have a problem. Okay, so this finishes our consideration of the method, and now we go into the computer program, into the MATLAB computer program and the GAUSS computer program, and describe value function with the help of these computational programs that you can also download from my homepage. So the code is stored in the MATLAB program chapter 6 ak60value.m, and in case you're using GAUSS, chapter 6 ak60value.gss. So this particular tutorial here is on the GAUSS version. If you're using MATLAB, please switch to the parallel video that considers the same exercise here, but with using MATLAB. Now let me show you where you can download the GAUSS code. Therefore, we go to my home page. I'm sorry, it's still in German, so the university is building up the English-speaking sites. And you go to the home page of my book on public economics, where you find the material on the book. So I put this material for chapter 6 AK60 value also on my homepage for the book Public Economics, the Macroeconomic Perspective, because this video here is part of a graduate course on social security and dynamic general equilibrium, which basically uses chapter 6 of my book Public Economics, just this particular part on the value function iteration. The direct solution of the Auerbach-Kotlikoff model is taken from the book Dynamic General Equilibrium Modeling from Alfred Mausner and myself. So you find this particular code on my home page. Scroll down to my computer code here, download computer code. And locate the area where we have the particular links to the chapters. So this is on chapter 6, pensions, download zip code, in case you're using GAUSS. In case, of course, you're using MATLAB, just choose the other link. And when you download this zip file, there's a whole directory full of GAUSS computer programs. Just load them into a directory that you use for this course, and then open chapter 6 akvalue.gss in your GAUSS editor. It will need a couple of other input functions. So for example, we used the nonlinear equation, the optimization routine from toolbooks.src. So this should be in the same directory that your GAUSS computer code can work. All right. So let me switch into the GAUSS editor. If you have not already opened your GAUSS editor and loaded the program chapter 6 ak60 value.gss into your editor, please pause the video at this point and take your time to get all the material ready. So once you're ready, let's go on and debug our code. So you should have something like this in front of you, the GAUSS program chapter 6 ak60 value.gss, which uses Go in section search, and it includes a couple of source codes, toolbox source and function source, which should be in the same directory so that your the program compiles and runs. So let us try if your program in fact runs properly. So let's run the program here. And you can see the output on the screen. Q is the iteration over aggregate capital and employment. I is the individual age, so when we solve the value function iteration at age 20, 30, and so on. Of course, we go backwards in time, so it's 60, 50, 40, 30. And in the final column, you find the value of K and L, aggregate capital and labor, in your iteration Q. So, for example, the capital stock converges to 0.875 and the employment converges to 0.222 after 23 iterations over the aggregate variables, and it takes 35 seconds here with this computer. So everything is fine. Here's the output. That's when you're using 200 points for the grid over the individual capital stock. This is our consumption. As you can see, this is not very nice here. We know from our first order conditions that consumption in old age should rise linearly, so we should have a linear slope here, which is clearly not the case. So our
our illustration here, our figure points to the fact that our number of points, 200, is not large enough. We should choose a couple of more points, let's say 2000 or even more. And here's our labor supply, which is downward sloping over age, and it falls from 0.36 to 0.31, so approximately 0.35, 0.034 is the average labor supply over the lifetime. And these are our aggregate values. So we have an interest rate of 5%, so the discount rate is smaller. The discount rate is approximately 4% if we choose beta equal to 0.96. Our real interest rate is 5%, so this results in an increasing consumption age profile over time. And we have aggregate employment and of 0.223 in our model. Now let's get into the code. And therefore, let's debug the code. So we use the debugging function here in GAUSS and skip through the problem here. In the first part, just like always, we clear the memory, we clear all variable names, and we clear the screen, and we load our auxiliary programs toolbox.src and function.src into memory so that we can, for example, do something like optimization routines, run optimization routines. In line 30, you specify whether you use linear or cubic interpolation, and we decided to use linear interpolation. And I will skip the part that's doing cubic spline interpolation. Please check the book by me and Alfred Mausner on dynamic general equilibrium modeling for the details. And we use the variable name bsec to take the computational time, the initial time when the whole program started. In the next 10 lines or so, we calibrate the model with the parameters that you're familiar from the last video. So we have beta equal to 0.96, choose an initial interest rate of 4.5%, a coefficient of relative risk aversion of sigma equal to 2, alpha, our production elasticity of capital, is set equal to 0.36, a replacement ratio of pensions relative to net wage earnings is 30%, depreciation rate amounts to 10%, and we have 40 periods as workers and 20 periods equals to 20 years as a retiree. We calibrate the utility parameter gamma, which measures the weight of utility from leisure in the Cobb-Douglas function equal to 2, and we can compute the equilibrium income tax rate from the replacement ratio and the measures of the working and the retired agent respectively, which provides us with tau equal to replacement ratio over 2 plus the replacement ratio. This follows from the fact that the measure of the workers is 2/3 and the measure of the retirees is 1/3, and we have a ratio of pensions to net wages equal to the replacement ratio. Now, as I said before, we choose an asset space for the individual asset wealth from 0 to 10, and we use 200 equispaced points. So let's run to this grid here in our debugging mode. And our grid here, A, is specified as ranging from 0 till 10, and the grid points are approximately 0.05 apart from each other. We also specify a small constant here, AEPS, which is 1/200 of the first grid points. So this will be important to check for corner solutions. What we will do is we will compare value at 0, the lower limit of our individual asset space, and 0.000251, the value at this point, and compare these two. And if value at 0 is lower than the one at this point, AEPS, we conclude, okay, it's a corner solution. We use psi equal to 0.001 as our constant in the utility function, so that when we test for 0 labor supply, 0 income, and 0 assets, so that we have 0 interest income, will give us 0 consumption, or even negative consumption if we accumulate savings. Well, we do not want our computer program to break down at this point when we compute utility for consumption equal to 0. And in this case, we said, of course, if we use this constant here, psi, our utility function will not break down, because then consumption from utility, and is particular marginal utility of consumption, is not equal to minus infinity. Plus infinity. Okay, then we use phi again to update our aggregate variables, just like in the case with direct computation. And we specify the tolerance of 0.0001 for the aggregate capital stock, and the tolerance 1 to the power minus 10 as a tolerance for the GAUSS section research. If your program takes too long, you might try to reduce the tolerance here for this optimization routine. So we look for the maximum, and this tolerance here describes the difference between the last 2 iterations over the variable x when we want to find the maximum of f of x. And we need to initialize our value function, as you will see shortly, and we use a very large negative value, minus 1 to the power 10, e to the power 10, 10 to the power 10, sorry, exponential 10. We initialize aggregate labor again with 0.2 and aggregate capital, so that it implies an interest rate of 4.5, which gives us a value of aggregate capital stock K bar equal to 0.828. We iterate over aggregate capital and labor at a maximum of 30 loops, NQ equal to 30, and we store the results for aggregate capital and aggregate employment in the vector KQ. Okay, here's the outer iteration. That's step 1 and the steps 7. In step 2, we computed aggregate wage and interest rate and the pension level. That's step 2. As you can see, this is very short. And now comes the big step, the complicated step, to compute the optimal individual policy functions. Therefore, we set up the policy functions and the value functions. We store them at our asset grid. So we store, for the retired agent, we store the value function over 20 periods at 200 grid points. So the first arguments are the grid points. The second argument is the retirement period. And we do the same with the optimal policy with regard to next period assets. Call this vector AR opt for assets of the retired optimal, and also CR opt, so for the retirees optimal consumption. And now comes the initialization of the value function in the last period. So in the last period, when we have asset A60 at this amount, well, our consumption is wealth times 1 plus interest rate plus pension. And this provides us with the utility as specified in the procedure U. So let's go down into this procedure. And we compute the Cobb-Douglas utility in this procedure U. So let's return. And we store the utility at age 60 given wealth A of L. So in this case, we do the loop. Our first grid point is 0. Our second grid point is 0.05. We always compute the interest income plus the pension income, set it equal to consumption, and compute utility of consumption and leisure equal to 100%, and store the values in the value function. And for our optimal consumption, we store our consumption A of L times 1 plus R plus pension. We do this over those 200 points, and everything is stored here in the value function we are. The value function and the policy function of the worker are initialized with 0. And now we start to iterate backwards in time. So that's the idea of Richard Bellman in his dynamic program. We've initialized the value function in the last period of life at age 60. And now we compute the optimal lifetime utility at age 59, our value function. And we use the value of the value function at the grid points in period 6 to compute it. So let's start the loop. I is our age. Our age now is 19. So the 19th period of retirement, which corresponds to the 59-year-old household. And we look at the first grid point. Our loop over L are all the grid points on our asset space. And our first grid point, of course, is 0. We assume that we have a credit constraint, so households cannot accumulate negative wealth here. And we initialize the variable ax, bx, cx as follows: ax equal to 0, bx equal to -1, and cx equal to -2. We will see in a moment why this is appropriate. We set the initial value equal to the negative value, v0. Now we do a grid search over the individual asset points at point A1, A2, A3, up to A200 over the whole asset grid to find the interval that contains the maximum. So for our golden section search, we need the lower bound A and the upper bound D in our figure, if you remember, which contains the maximum. And then we need additional values, additional points between these two limits, A and D, in order to shrink the interval around the maximum. And therefore, we want first to find in which interval does the optimal next period asset is located, and therefore we look over all grid points that we have. So we start with the grid point A of 1, which is 0, and then we increase the grid points one by one in each iteration, and this iteration has the index, the variable m. So we compute the value of the value function at the first grid point, A of m, with m equal to 1. And let's compute this. So go down into value 1. Okay, we are looking at the value function at age 59 at the grid point A of 1, which is 0. And we check what is the value of the value function if we choose the right-hand side of the Bellman equation, if we choose x equal to 0. So we get the asset level 0 at age 59, and we want to compute the value of the right-hand side of the Bellman equation in case next period asset level is also 0, and therefore we obtain, next period we obtain the value function at A60 equal to 0, and discount this value function by the discount factor beta. Okay, first we check if c is smaller than 0, then we stop, because we have these problems that we cannot evaluate the utility for c smaller than equal or smaller than 0. This is not the case. C is equal to 0.0835 for our choice of this and next periods, both equal to 0. And we compute the right-hand side of the Bellman equation. It's the sum of utility HH59 and discounted utility, a discounted value next period with the capital stock x equal to 0. So V1 is now the right-hand side of the Bellman equation if the next period capital stock is chosen to be 0, which of course implies consumption C that we just used in our computation. And the value function, the right-hand side of the Bellman equation is minus 21.225 in this case. So now let's run it to the next case where we compute the right-hand side of the Bellman equation if next period worth is equal to 0.05. So this period, at age 59, we now have asset level equal to 0. Next period, we have wealth equal to 0.05. And let's compute what this implies for our value function. Well, in this case, the value function is minus 34.21. So it's lower, the right-hand side of the Bellman equation is lower than if we choose 0 for next period capital stock. Accordingly, we already have bracketed the maximum. Remember that if the value function decreases, well, we know that the maximum has to be on the left-hand side of the present value. So it has to be on the left of 2, so to the left of 0.05. So in this case, we set the upper interval for the GAUSS section search equal to this point, which is 0.05. In the former loop, our V1 was larger than V0, so minus 21.225 was larger than the large negative, and therefore we allocated AX to A of 1 and BX to A of 1. Okay, and then we are done with this loop. And now we compute the optimal value function. So we know that the maximum must be somewhere between 0 and 0.005. We have the first case that the second grid point is already the Bellman equation, the right-hand side is already lower than at the first grid point. Therefore, we have to check if it's a corner solution. So here we have the case that we have to check whether the value function at 0 is larger or smaller than at 0.00251. If it's larger, then we know we have a corner solution, or can be pretty sure, because at 0, next period capital stock 0, we have a higher Bellman right-hand side than if we choose 0.0025. So for our accuracy that we assume this is fine. Let's see if this is the case. Yes, this is indeed the case. So we choose the next period capital stock equal to 0. Okay, and let's see what's happening if we have a normal case. So let's go to the next loop. We allocate this here. We save this optimal policy function. So our next period capital stock, our optimal is 0. And we save it to the variable opt to the optimal policy. We save the optimal value of the value function in our matrix VR of the optimal lifetime utility, the value of the value function, and we save optimal pensions. Now let's go to the next loop, next iteration. Now we compute the value function at the second grid point, and the second grid point is a equal to 0.050251. And we do the same computation over again. So if at age 59 our initial capital stock, our wealth, is equal to 0.05, what is the value of the right-hand side of the Bellman equation if next period at age 60 we have 0 wealth? Well, this is computed with the help of value A1, and it's minus 16.69. Again, this is higher than the high negative, minus 10 to the power 10. So we allocate this at 0 becomes our new maximum, and we save the new lower interval limit here of our goal section search equals to a of 1 equal to our low point 0. We save the maximum in the variable v0, and we go to the next loop for next period wealth at age 60, so that a of m is equal to 0.05. And let's go into the procedure value 1 again, which is the right-hand side of the Bellman equation. We again compute consumption if this period asset is 0.0525, and if next period the wealth at age 60 is also 0.05. Our consumption is larger than 0, so no problem. And we first compute the utility that's associated with consumption equal to 0.085798 and leisure 1. And next we compute the value function next period for our next period asset level 0.05025. And in the procedure R value, the retired agent's value function, we compute the interpolated value of the value function for capital stock K, or individual asset A, in the period T0. So T0, that's next period value function here, that's when we are retirement age 20. And here you just find, in the following, you just find the code for linear interpolation. So that's not really something fancy. Here you have the linear interpolation of our function. Okay, and this provides you with the value v1. Let's compare it to the right-hand side of the Bellman equation, when next period assets is 0. And as you can see, it's still larger, so we allocate the value 0 to the lower threshold. We have to provide an intermediate value here, bx, for the goal section search, and cx is still minus 2. And we continue to do this loop until our new right-hand side of the Bellman equation, v1 here, it's minus 30, is below the old maximum, minus 16. So we know that at the point A3, our value function, our right-hand side of the Bellman equation is already decreasing, so our optimum must be to the left of A3. And we store, therefore, A3 as our upper limit on the goal section search interval as our point C, our point Cx. And therefore, we are done with this search over the interval on which we apply the GAUSS section search. We do not have the case of a corner solution, neither at the lower limit a equal to 0, nor at the upper limit a equal to 10 to the largest limit on the individual wells. So what we do now is we use the golden section search algorithm to compute the maximum of the right-hand side of the Bellman equation, which is computed in the procedure value 1 in the limit 0 and 0.1, and we also provide a midpoint 0.05. And we ignore the details of the GAUSS section search algorithm. You will find them in our book on dynamic general equilibrium modeling. So we provide lower limit, intermediate point, and the tolerance here for the difference between the last two steps in the state space here. And this solution is stored in AR_opt. In our case here, it is 0.0295, and as you can see, of course, we have found an intermediate value, an interior value between 0 and 0.10. Our value 0.0295 is just fine in this interval, and we store this value for the optimal policy and our value of the value function at this point and our optimal consumption. Okay, and that's all that we need to note with respect to the value function iteration over the 20 years of the retiree. And now we do this. Let's look at the optimal on the Bellman equation of the worker. The same logic applies, and here's we start. Let's go to line 201. Run with the cursor to the line 201. We initialize the value, the right-hand side of the Bellman equation with minus 1 times 10 to the power 10. And then we compute the right-hand side of the Bellman function at this point k0 equal to 0. And next period wealth equal to 0. So let's go into the right-hand side of the Bellman equation here. And as you can see now, there's a new line. We have endogenous labor supply. Our labor supply, you know, line 452, you know this is our first order condition on labor. We have to check if this is smaller than 0. No, it's not. Our optimal labor supply is 0.332. In case it were smaller than 0, we would set it to 0. And in case it were larger than 1, we would set it to 1. We can compute consumption. So we have labor income 1 minus tau times W times N. We have interest income R times A. A is equal to 0. And we have next period assets level of 0. So this gives us consumption equal to 0.308. It's larger than 0, so we have no problem that the computer code will bug. And we use linear interpolation, and therefore we provide a the computation continues in line 46.3. Now we have to make a distinguish between the case that next period we are retiree. Therefore, we need to use the value function of the retired R value at age 1 in retirement, which means age 41 in real life. Sorry, 61 in real life, first period of retirement. In case we are we have a worker whose age is below 40, we get to this line here, and there we have to compute the Bellman equation with the help of the value function of the worker, W value. So these two cases needs to be distinguished. Here we have the real value function, which we already know from last time. Let's go to the case where we compute W value, the value function of the worker. So place the cursor in line 466 and press run to cursor. Okay, now we consider a case where our period is 39, which corresponds to real life age 59. We are a worker in this period and we are also a worker in the next period. Therefore, we need to consider the value function of the worker at age 40 in our Bellman equation next period value function, and this is done in the line 466. So we compute first the utility here, and next we compute the value of the worker's value function with capital stock 0 and at age 40. So we are at age 39 right now. In the Bellman equation, we have to look up the value of the value function at age 40. And again, we just do a linear interpolation here and return the interpolated value at age 40 for capital stock K. All right, and the rest is as before, as in the case of the retire agent. We just search over the asset grid, iterate over M from 1 up to 200 and find the interval, the limits that bracket the maximum. Now there's an additional element here in this code that I would like to mention, which is in line 202. Now we know of certain properties, qualities of the value function. So for example, we know that it's monotone increasing in the asset level, and we also know of the optimal policy function that it increases with asset. So richer agents also choose a higher wealth level next period, not surprisingly. Therefore, we do not have to start our iteration over the individual asset space at M over the asset grid at point 0. But for example, if we found in the last iteration that, well, the optimal capital stock, next period capital stock is 4.0, we do not need to start for a wealthier household at 0 again, but we start at approximately 4.0 to bracket his maximum. So we do not start all at the beginning, but we start at a value which is close by, and in fact we store this in the variable M0. So if in the last iteration our optimal asset grid is on the grid point M0, then in this iteration, well, we start looking at M0 minus 1 to find the new interval that brackets the maximum. Okay, and the rest then is straightforward. So let's run to the cursor, which takes a couple of seconds here. We have computed the optimal policy function, the value function for the retired agents and the workers up to age 1. And now we want to compute the wealth age, labor supply age, and consumption age profile. And we know that in the first period, our individuals have 0 capital, 0 wealth. And therefore, we can just iterate over the age, over the lifetime periods of the households. Now it's forward iteration, starting at age 1. We know we have wealth 0, and now we compute in line 261. We compute the optimal savings that's associated with a wealth level of 0 at age 1 and allocated to the wealth level at age 2, which is equal to 0.02561. We store this, we compute the labor supply here, we compute consumption and store all these values. And at age 3, we compute again. At age 2, we compute again the optimal wealth at age 3 and save them and iterate forward over time to compute our wealth, labor, and consumption age profiles. And when we have done so, we just compute the average wealth as our aggregate wealth and update capital stock as a weighted average of the initial aggregate capital stock and the new found solution, and the same for aggregate employment. Notice that the measure of the workers is 2/3 times the average labor, which implies aggregate labor. And we iterate over this capital stock until we have found a solution, and that's what I showed to you in the beginning. So we have the aggregate capital stock equal to 0.86 or 7, something like this. And we also have computed a couple of other values, for example, the value of the value function and the aggregate employment, mean consumption, stuff like this. All right. So let me summarize what we did in the Gauss computer program, chapter 6, akvalue.gss. We used the insights of Richard Bellman from the 50s when he was doing work on dynamic programming, which is also some mathematical insight and also some computational insight. And the great idea about his Bellman principle of optimality was that he could split up the optimization problem over many periods, over many variables into one, where we just look at this period and next period, this age and next age, and therefore reduce the space of controls from, let's say, all 60 consumption levels over your life and the 40 levels of employment to one where you just consider one period, for example, at age 20 when you're a worker, and just choose this year consumption and this year labor supply, which implies also, because of the budget constraint, with the help of the budget constraint, next period wealth. And then you just look up what is the value of my value function associated with this wealth level, and you're done. So you reduce this huge scale optimization problem into sub-problems which just consider this and the next period. And if you're using this recursive structure starting in the last period of life, it's very easy to compute the solution, and you have to tabulate the values in each year going backwards in time. Now, you might also know this kind of Bellman equation from problems with infinite time horizon. So, for example, if you look at the Ramsey problem, there you cannot go back in just one loop because you do not have the exact value at the end of life. That's with finite lifetime. In the last period of life, when you're age 60, you die the next period, you know exactly the value in last life, you can compute it at asset points. With value function in infinite time horizon problems like the Ramsey problem, this is not possible because there is no last period. So you have to make a guess of this value function, and by the so-called contraction mapping theorem, you know that it converges nicely to the solution. So this is, of course, a neat advantage of finite lifetime dynamic programming. You start with the more or less exact solution at the grid points in the last period and can work your way back in time, and you do this just once. On the other hand, of course, you have to store much more variables because, for example, you have 60 years and you have to store the value function at each age. In the Ramsey problem, you don't if you look at the steady state, because then the value function is, of course, constant. Now, this insight has helped us to compute problems with the help of value function, and we have notice that this is much more time consuming than using direct computation methods like using nonlinear equation solvers, the Newton-Raphson algorithm. But with the Newton-Raphson algorithm and these nonlinear equations, there are two major problems. First, you need to have a structure or a number of heterogeneity in the model that's manageable. So just one or two or three productivity types, but not switch in productivity types. And sometimes if you have large-scale overlapping generation models with a couple of hundred variables, you have to come up with an initial guess for the solution of this nonlinear equation problems. And this is by no way trivial. And we will consider this in the next video, in the next two videos. So to summarize my experience here with these two different computational methods, always use the Newton-Raphson algorithm, the nonlinear equations, if possible. It's more accurate, it's faster, and you can be much more secure, much safer with your solution and with the interpretation of the results. If you have heterogeneity, if you have stochastic income, it's impossible to use Newton-Raphson. You have to rely on value function iteration. Now, value function iteration is slow, especially with MATLAB. I therefore hardly use MATLAB for these problems. I have provided you with this, will provide you with a solution to MATLAB, but I prefer GAUSS. But even GAUSS may be too slow. So co-authors of mine, they use Julia or Python. So Julia speeds up the computation by a factor of 10 approximately in comparison to GAUSS, and Fortran is also a method that's much faster than GAUSS. So this is an alternative, and you may consider these software type, in particular Julia and Python are free software, shareware, so that's of course very convenient. If you consider more complex, high-dimensional state space problems with overlapping generations.